All right, so what we're going to do in this video is work through a few examples of proton NMR spectra of relatively simple compounds to work on recognizing different peaks and assigning each peak in the spectrum. This is sort of the culmination of all the different techniques that we've learned in this chapter about how to look at these types of spectra. So if we start with the compound over here on the left, this ketone, first tactic that you would want to do is try to understand how many signals you would expect out of the proton NMR for this compound. If I look, I would pretty quickly recognize I've got a series of hydrogens at this methyl group A. There is a CH group here at B, and then two equivalent series of protons corresponding to those two methyl groups as C. If we think about splitting in terms of what we would expect based on neighborings, we should expect methyl group series A should turn out to be a singlet because it has no hydrogen neighbors on the carbon next to it, so this would be a singlet. If we look at the signal C, those 6 hydrogens causing that signal have one neighbor on the neighboring carbon that holds those two methyl groups. So that one hydrogen would split the signal for those 6 hydrogens into a doublet. Signal B is by far the most complicated because it has a large number of neighbors, so I get one signal for that single hydrogen on CHB plus its 6 neighbors. So I would expect, for following the n+1 rule, B should be what we would call a septet. So that should be a series of 7 little peaks. If we want to think a little bit about integration, what we would expect in this case was for singlet signal A, 3 hydrogens causing that signal. That should be an integration of 3 hydrogens. The septet B, since it's only one hydrogen on that CH, that would integrate to 1 hydrogen. And then, of course, the 6 hydrogens for the 2 chemically equivalent methyls would integrate to 6 hydrogens in this case. And so what we would expect is if we look for each of these things in the spectrum below, we would pick out the septet here. That's going to correspond to signal B. Makes sense because it's small. It gives us 1 integration. If we count those number of peaks, you really see 1, 2, 3, 4, 5 of them. You can kind of see the 7 on the much smaller peaks at 6 and 7 on either side of that multiplet. The chemical shift of that position makes sense. It's the farthest downfield because it's one of the 2 signals that are closest to the only electronegative portion of the molecule that we have, which is the carbonyl. The singlet at 2 parts per million, that's going to correspond to signal A, that CH3 group, because it has no neighbors. And then if we look down here at 1, the lowest chemical shift of the 3 signals, that's going to be the hydrogens corresponding to those 2 methyl groups that are 1 carbon removed from the carbonyl. And so we would be able to indicate that doublet as C. And so we can, using the combination of chemical shift and splitting patterns, we can actually assign all 3 of the peaks in this spectrum. All right, so what we're going to be doing here is sort of ramping up complexity as we move through this list of spectra. So if we look at this ether, again, first thing we would want to do is recognize number of signals that we have. So 2 equivalent methyl groups, those 6 hydrogens, should correspond to signal A. That neighboring group, that CH, methine, that's going to be signal B, should correspond to only 1 hydrogen in terms of integration. If we look on the other side, the ethyl group is comprised of a CH2. We can call that signal C. That should correspond to only 2 hydrogens. And then the methyl group on the end, call that signal D. That should integrate to 3 hydrogens. Now if we do the neighbor analysis for the splitting, what we should see with signal A, 6 equivalent hydrogens with 1 hydrogen neighbor on carbon B. So I would expect that signal to present as a doublet. If I look at signal B, I have 1 hydrogen causing the signal with 6 neighbors. I would expect that to manifest as a septet, so 7 small peaks in a series. If we look over at carbon C, I have 1 signal for those 2 hydrogens at the CH2 plus the 3 neighbors, so that would turn out to be a quartet. So 4 peaks together. And then finally what we should see with signal D would be 1 signal for those 3 hydrogens plus the 2 neighbors. That should show up as a triplet. Okay? So we know essentially what types of peaks we should be expecting from our analysis of the structure. Now we need to turn to chemical shift. If we look at chemical shift in terms of which signals we would expect to be farthest downfield, those are going to be the hydrogen signals that neighbor that electronegative oxygen. So signal B, that single hydrogen signal B, is attached to a carbon holding an oxygen. That should be one of the farther downfield signals. Same thing for this CH2 on the other side. It's attached directly to an oxygen. We would expect that signal to come farther downfield than the others. And so if I look in this region where we have signals a little bit farther downfield, what we should be able to note is that I have 2 signals there. I have one that is a series of, it looks like 7 little peaks. That signal corresponds to the methine signal B that should manifest itself as a septet because of its 6 neighbors. And then the next farthest downfield would be a quartet, as we would expect for the CH2 directly attached to the oxygen. So we can call that one signal C. Okay. The only other series of peaks we have are down here between 1 and 1.5. That's going to correspond to the 2 other signals that we have to assign in this case. And so this is a situation where the chemical shift of the methyl on one side and the pair of methyls on the other side are almost identical. So we're starting to see those peaks overlap with one another and start to sit on top of each other. But you can still look and pick out the doublet that corresponds to signal A, which those 6 methyls, and you can see that triplet that would correspond to signal D. So we can, taken together, go through and assign all of those peaks for this spectrum. Okay, so if we take a look at another ether, this one's again ramping up the level of complexity. Again, the first thing we want to do is go through and label the different peaks. So I have a CH3 attached directly to the oxygen. That's going to be chemically distinct from this CH3 on a neighboring carbon. We have a CH, which we can call signal C, a CH2, which we can call D, and then a CH2 holding a chlorine, which we can call E. So we have 5 independent signals that we have to work through. Signal A we would expect to integrate to 3 hydrogens, and because that series of 3 hydrogens has no neighbors on the neighboring atom, oxygen, we would expect this to show up as a singlet. B, again, also a methyl group, should integrate to 3 hydrogens, has 1 hydrogen neighbor on carbon C, so I would expect that series to appear as a doublet. Carbon C should have a complex splitting, right, because I get 1 signal for that CH plus 3 neighbors on the left and 2 more neighbors on the right. So the N plus 1 rule gives me 1 signal plus 5 neighbors. I would expect this to integrate to 1 hydrogen and appear as what we would call a sextet, so 6 little peaks. D should also have complex splitting. It will integrate to 2 hydrogens because it's a CH2. D has 1 neighbor on its left and 2 on its right. So that would be N plus, so 1 signal for the hydrogens on D plus 1 neighbor, 2, 3 neighbors. So I would expect that compound to show up as a quartet. So the hydrogen signal D should show up as a quartet. Okay. And then finally, signal E, again, integrates to 2 hydrogens. One signal for those 2 hydrogens plus its 2 neighbors. I expect that to appear as a triplet. Okay, if I think about chemical shift now, there are really 3 signals that we would expect to be far downfield based on what they're next to. So I would expect the CH3 group directly attached to the oxygen to be rather downfield. I would expect this CH group also attached directly to an oxygen. That should be farther downfield. And then the other series of hydrogens at this CH2 on carbon E should also appear downfield. And so I've got these 3 signals in that range that I need to parse out, and I can do that easily just by looking at the splitting patterns. So if we look at signal A, that should be the singlet that appears up here. So this should be signal A. E is the one that should appear as a triplet. It's also attached to the most electronegative atom on the molecule, so I can assign this triplet at farthest downfield as E. And then the heavily split signal of C should also be downfield because that carbon also holds an oxygen, so I can assign that signal here. So just like that, we're able to assign 3 of the 5 signals right away by combining splitting and chemical shift. If I look at the remaining ones, I have a quartet and I have a doublet. Our analysis tells us that methyl group B only has 1 chemical neighbor, so that should be the doublet that we see farther upfield because it's not in an electronegative environment. And then the remaining signal that we haven't assigned yet is a signal D, which again, based on its 3 neighbors, should appear as a as a quartet, and so that will be signal D. So once again, we can use that combination of chemical shift, splitting pattern, and expected integration to assign these peaks. I think in these cases, really, chemical shift is secondary actually to the splitting pattern. Splitting pattern really tells you everything you need to know about these things, but we can use the chemical shift table to justify the relative position of each of those signals. All right, so now we're sort of increasing in level of complexity again. If we want to think about mapping out the distinct signals that we would expect for this system, let's start on the left-hand side. I have a methyl group A, which is chemically distinct from CH2B. CH2B is distinct from C because C is directly attached to a carbon that's involved in a carbon-carbon pi bond. This hydrogen on the carbon-carbon pi bond, D, that's distinct from the methyl attached to that pi bond, E. And then we have a series of equivalent protons, F, on either side of this aromatic ring. G also are 2 equivalent signals, and signal E. Okay? And so those are the expected signals that's the number of signals we would expect. And now let's see if we can pin down which ones are which based on expected splitting patterns and chemical shift. So the first thing I want you to note is the presence of signals in this 6.5 to 8 region that correspond to hydrogens directly attached to an aromatic compound. And it actually turns out that all 3 of these signals, F, G, and E, appear in that range. So this subset of peaks all together, we're not going to worry about specifically assigning each one because it's clear that the splitting pattern is a little bit weird. All of those taken together are the 5 hydrogens that sit on that aromatic ring. So we can actually assign all of these as F, G, and H right away. Okay? The next farthest downfield peak is going to be this small little triplet here. or this small little multiplet that we see here, that's going to correspond to what we call a vinylic position. It's the only one that falls in this range here between 4.5 and 6.5. So this peak directly attached to a carbon double bond, that's going to be hydrogen D. We can rationalize that D should be a triplet because that hydrogen D has 2 neighbors on carbon C. So that should be a triplet. All right, so what we've done now is assign all of the peaks that are farthest downfield. So we've taken care of signals at the following places. We've assigned all 5 signals on that benzene ring, and we've assigned this hydrogen on the carbon-carbon double bond. Now we can pause for a second and take a look at splitting patterns. If we look at signal E, we would expect signal E to appear as a singlet, as it has no hydrogen neighbors on its neighboring carbon of that carbon-carbon double bond. If I look at the remaining signals, the only singlet that I have here is this one, E, at a chemical shift of about 2, which is consistent with a position in this allylic position that we have. All right, so next we have C. C is another one that's in an allylic position, and it's splitting. I would expect to get 1 signal for those 2 hydrogens plus 2 neighbors. So I should expect for this, actually it's plus 3 neighbors, right? I have C. If I look at C, it has 1 neighbor here and 2 neighbors here. So I should expect this to appear as a quartet. And what we see for signal C, we can actually see that little quartet here buried underneath the singlet that's coming from signal E, which I didn't write my E very pretty. And so that takes care of signal C. The remaining ones that we have to look at are B and A. B should be highly split. I get 1 signal for B plus 3 neighbors on the left and 2 neighbors on the right. So I would expect that to be, so that's going to be 5 neighbors. I would expect that to be a sextet. The only sextet that we have in the series is going to be B here. And then the final one, A should be a triplet because I have only 2 hydrogen neighbors on carbon B. So I can assign this final peak as A. So again, that combination of thinking about chemical shift and splitting allows us to assign every peak in this spectrum. The key here is always going to be being systematic about it, labeling everything, and following what the data is telling you. All right, so another one here. Let's go through and label the peaks that we have in the system. So if we start with this methyl group holding attached to the oxygen that we can call signal A. We have hydrogens on this aromatic ring, which I'll go ahead and draw in. They're all chemically distinct, so we call this one B, this one C, and this one D over here on the right-hand side. Remaining signals that we have is we have a hydrogen directly attached to the nitrogen. We can call that signal E. We have a methyl group with 3 hydrogens directly attached to the nitrogen. We call that F. Then we have a CH2CH3 over here next to the ketone. We can call that G and H. Okay. All right, so if we look at these series of signals, we need to start thinking about what we would expect in terms of their splitting and maybe also their chemical shift. So if I look at A, signal A should integrate to 3 hydrogens. It has no hydrogen neighbors on the oxygen, so I would expect that to appear as a singlet. Hydrogens B and C, because they're on this aromatic ring, things can be a little weird. They can sometimes split each other. Sometimes they will sit on top of each other depending on the strength of the instrument we're using. As it turns out in this case, those hydrogens are going to end up sitting on top of each other in this case. So B and C, they're going to each integrate to one hydrogen, but together they'll be two hydrogens. And actually they turn out to be singlets just because those signals sit on top of each other. We'll talk about assigning that in just a minute. If I think about the NH hydrogen, E, that should integrate to one hydrogen. Turns out those hydrogens directly attached to heteroatoms like a nitrogen or oxygen, they can exchange rapidly in the solvent, and so what ends up happening is that they don't split anything even if they have neighbors. And so those types of hydrogens, OHs and NHs, those are always singlets. Okay. F, again, because that other neighbor on nitrogen gets exchanged, F is going to show up as a 3-hydrogen methyl group as a singlet as well. D has no hydrogen neighbors, and so that should integrate to one hydrogen and show up as a singlet. And then our final two that we have to think about, G and H, that's a standard an ethyl group, so CH2 next to a CH3. So G as a CH2 should integrate to two hydrogens because it has 3 neighbors. That should then show up as a quartet. Methyl group H is going to integrate to 3 hydrogens. It has 2 neighbors. It should appear as a triplet. Okay. So we've gone through and found all the different hydrogens. We've mapped out a little bit about their splitting patterns. And now we need to think about chemical shift in terms of trying to assign each of these things. So where we'll start, let's actually start with H and G, because I think those are the easiest ones because those are the ones that have a splitting pattern that we can hold on to. So H, 3 hydrogens attached to a CH2 that has 2 hydrogens. I should expect to see H appear as a triplet. The only triplet I have in this system is this one down here at 1. Makes sense that it's at 1 based on the chemical shift that we would expect for a series of hydrogens that are not directly attached to anything electronegative. G will be a signal that integrates to 2 hydrogens. That signal has 3 neighbors. I would expect that to be a quartet. The only quartet that I have in this system is here. So I can call that G just based on the splitting pattern. But that chemical shift of 3.5, it makes sense based on its position in an allylic position near that carbonyl. Okay, we got 2 signals that should integrate to 3 hydrogens as singlet methyl groups. I have a singlet methyl group in A, where I have a methyl directly attached to an electronegative oxygen. And then I also have signal F, a methyl group attached directly to a less electronegative nitrogen. And so of the 2 singlets that I see here and here, I can assign the one farthest downfield to A because oxygen is more electronegative than nitrogen, and this signal I can assign to F. Okay. So if we think about what we've assigned H, we've assigned G, we've assigned F, and we've assigned A. All that we have left now are going to be the aromatic compound, the aromatic hydrogens B, C, and D, and then also this extra hydrogen that sits on nitrogen. I can assign this little peak here that's a little bit broader, that I can assign to E as the hydrogen directly on the nitrogen. So by virtue of the fact that that nitrogen-hydrogen bond can exchange with solvent, it can pop on and off of the compound. We don't see that signal ever getting split by any other signal, but we also see it broadening. So the fact that that little peak is a little bit broader than the others, that clues me into this being the signal that corresponds to E. The remaining signals in this region of 6.5 to 8 in the aromatic range, these remaining signals I can assign as B, C, and D. And we don't have to split hairs about which one is which. but I can recognize that because I have that series of signals in that 6.5 to 8 range, I know that that corresponds to the benzene ring. So I can all together go through and assign each signal in the spectrum. Okay. Here's another one. If we want to look at different types of signals we would expect here, 2 equivalent methyl groups, I would call this A. This CH would be B. Got a series of hydrogens on the aromatic ring, C, D, and E again. I've got a hydrogen F on this aldehyde. And I have a CH2 here, which I can call G. And I have one hydrogen on the OH of the carboxylic acid, which we'll call H. All right, and so if we think about what we're expecting in these cases, the easiest ones I think to deal with at first are going to be C, D, and E. Those are the aromatic ones. We only have 3 signals in this aromatic region, right? And so I think we can very easily call these 3 signals C, D, and E. And again, we're not going to split hairs about which one is which. So that takes care of those. We can rely a little bit on chemical shift here to assign the 2 peaks F and H on the aldehyde and carboxylic acid. Again, the aldehyde F, that turns out to be right here in this 10 region, so this is F. And that OH, that hydrogen directly attached to the oxygen of the carboxylic acid, that's going to be really far downfield H, because it's attached to a carboxylic acid carbonyl, so that gives me that diamagnetic anisotropy that pushes that all the way downfield to 12, but also directly attached to a heteroatom. All right, so what do we have left now? If we look at that, the ones that we have left to think about really are just A, B, and G. And these should be easily discernible based on splitting. G has no hydrogen neighbors, so it should be a singlet. And it should have a pretty far downfield chemical shift because it's flanked by a carbonyl on one side and an aromatic group on the other. So I can assign this singlet as G. And then B should be split by its 6 neighbors into a septet, so I can call this little septet here B. And then A should be split into a series in a doublet based on the 1 neighbor B, so I can call this one A. So in this case, we really had to rely a little bit more on the chemical shift of the sample rather than splitting pattern, because a lot of this molecule has very simple splitting pattern. If we move on to the next one, this is one where we'll